Hi everyone, today we're going to be going over an in-depth example of Lewis structures using the molecule PO4 3-. So first we're going to start by finding the electron configurations of each of the elements in this molecule. So phosphorus has 15 total electrons, but we're going to be using the noble gas shorthand. So the noble gas right before it is this neon right here. And then since we are in the third row, we have our S group right here and our P group over here. So we have 3s2, and then it has 3 electrons in the P group. Now similarly for oxygen, which is right here, the noble gas before it is helium. And so it has these 2 electrons, so it has 2s2, and then it has 4 in the P block. So those are our electron configurations for phosphorus and oxygen. Now to determine the number of valence electrons, those are the electrons in the outermost shell, so that's just the total number right here and here. So phosphorus has 5 valence electrons, because those 2 right here are the 3 plus. And oxygen has 6 valence electrons, 2 from the S, 4 from the P. So now for the total number of valence electrons in our PO4 3-, we have 1 phosphorus, so that's 5 valence electrons, plus 4 oxygen, so that's 6 times 4. And then since we have this 3- charge right here, that adds on 3 more electrons to give us a total of 32 valence electrons. So now we are ready to draw our Lewis structure. So we're going to put the least electronegative element in the middle. That will be our phosphorus. And then we'll surround it by the other elements, oxygen. And then we'll add single bonds in between each phosphorus and oxygen. So that used up 8 of our valence electrons, which means we have 24 remaining. So we can go ahead and add lone pairs around each oxygen to give it a full octet. And then that used up all of the remaining 24. But let's take a look at our formal charges on each element. So recall formal charge has the formula valence electrons minus non-bonding electrons, so those lone pairs, minus 1/2 of the bonding. So that means we count this as one of the bonding, but then we do multiply it by 1/2 to just count that one that's attached to the oxygen or the phosphorus. So for phosphorus, we have 5 valence electrons, 0 non-bonding because there's no lone pairs, and then minus 1/2 of, we have 8 electrons that are contributed from the bonding because 2 from each bond around that phosphorus. So that leaves us with a +1 charge for phosphorus. And all of our oxygens are the same, and they have 6 valence electrons, minus 6 non-bonding because 3 lone pairs with 2 electrons each, minus 1/2 of 2 from each of these bonds right there. So that leaves us with a -1 charge on each oxygen. Now, in theory, this could be correct because we still have that overall charge of -3 because this +1 will cancel out with one of the other -1s. But let's see if we can figure out a way to reduce the formal charges. So what we can do is we can form a double bond. So we're going to take one of these lone pairs from the oxygen, it doesn't matter which oxygen, and we're going to make it into a double bond here. So now the oxygens still have a full octet, but phosphorus has an expanded octet, which is okay because that follows one of our exception rules. So now let's take a look at the new oxygen formal charge. So it still will have 6 valence electrons. Now it only has 4 non-bonding because it has 2 lone pairs. And then it has 4 from the bonding because there's a double bond, so that's 2 electrons per bond. So now its overall formal charge is 0 for just that oxygen. And similarly for phosphorus, it still has 5 valence electrons, still 0 from our non-bonding, but now it has 1/2 of 10 from our bonding because there's 1 bond, 2, 3, 4, and 5 total bonds surrounding that phosphorus. So its overall formal charge is 0. So that reduced our formal charges. So now this is a happier structure. So we have our Lewis structure and our formal charges done. We can move into geometry. Now to determine geometry, we have to consider the total number of electron groups. And that will be 5 because we have 4 total electron groups. Because this double bond is counted as 1 electron group. And since we have no lone pairs, that means that our electron domain geometry will be the same as our molecular geometry. And 4 electron groups, 0 lone pairs corresponds to a tetrahedral. All right, I hope that allowed you to understand a little bit more about Lewis structures. Thank you for watching.